Hello, Accelerated Chemistry students. This is Mr. Spurk, and this is your Chapter 17, Section 1 notes, all over the flow of energy. So first we're going to talk about energy transformations. Energy is the capacity for doing work or supplying heat. Unlike matter, energy has neither mass nor volume. Energy is detected only because of its effects. Thermochemistry is the study of energy changes that occur during chemical reactions and changes in state. Every substance has a certain amount of energy stored inside it. The potential energy, the energy stored in the chemical bonds of a substance is called chemical potential energy. The kinds of atoms and the arrangement of the atoms in a substance determine the amount of energy stored in the substance. So think about fuel. When you buy gasoline, or when you're in your whoever's vehicle and you're buying gas, you're actually buying the stored potential energy that the fuel contains. The controlled explosions of the gasoline inside the car's engine transform that potential energy into work, which can be used to propel the car forward. Heat is also produced, which makes the car engine extremely hot. Also, think about potential energy would kind of be like right when you wake up. Most days we all have very low potential energy, it seems like, but that's kind of a relation to potential energy. Energy changes occur as either heat transfer or work, or a combination of the two. Heat, represented by a lowercase q, is energy that transfers from one object to another because of a temperature difference between the objects. Heat flows spontaneously from a warmer object to a cooler object. If two objects remain in contact, heat will flow from the warmer object to the cooler object until the temperature of both objects are the same. So then we have endo and exothermic processes. So what happens to the energy of the universe during a chemical or physical process? Chemical reactions and changes in physical state generally involve either the absorption or the release of heat. You can define a system as the part of the universe on which you focus your attention. Everything else in the universe makes up the surroundings. Together, the system and its surroundings make up the universe. The law of conservation of energy states that in any chemical or physical process, energy is neither created nor destroyed, so that's similar to our law of conservation of mass. During any chemical or physical process, the energy of the universe remains unchanged. If the energy of the system increases during that process, the energy of the surroundings must decrease by the same amount, because the law of conservation of energy says that we don't lose any energy. So let's talk about the direction of heat flow. The direction of heat flow is given from the point of view of the system. Heat is absorbed from the surroundings. If the heat is absorbed from the surroundings, it is an endothermic process. Heat flowing into a system from its surroundings is defined as positive, and Q has a positive value. An exothermic process is one that releases heat to its surroundings. The heat flowing out of the system into the surroundings is defined as negative, therefore Q has a negative value. For an endothermic process, think about sitting near a fire or a heater. That heat is flowing into the system, or it's flowing into you. You're feeling the heat. You are warming up. An exothermic process would be like, think of like working out. The heat is flowing out of you. You're sweating because you're getting warm, so the heat is radiating away from your body. That's an exothermic process. On a sunny winter day, the snow on a rooftop begins to melt. As the melted water drips from the roof, it refreezes into icicles. Describe the direction of heat flow and the water that freezes. Is this process endo or exothermic? So in this situation, we're going to say that our system is the water and the surroundings are the air. So let's remember that heat flows from a warmer object to a cooler object, and endothermic processes absorb energy or heat, and exothermic processes release it. So in order for water to freeze, its temperature must decrease. Therefore, the heat flows out of the water. So freezing is actually an exothermic process. Think about another example could be like an ice pack. An ice pack feels cool because it's actually removing heat from the surroundings. And the chemical reaction taking place within the ice pack is endothermic. It's drawing heat into the ice pack, which is why you feel its cool effects. So heat flow is measured in two common units, the calorie and the joule. A calorie, which we abbreviate as CAL, is defined as the quantity of heat needed to raise the temperature of 1 gram of pure water 1 degree Celsius. So 1 calorie with a capital C, and that is actually a dietary calorie. So when we, in common our common speak, when we say calories, we're typically talking about food. That is the capital C, calorie, and that's actually equal to 1 kilocalorie with a lowercase c, which is 1,000 calories. So in science, we talk about the lowercase calories, and in dietary science, we talk about the capital letter C for calorie. The joule is what we will be focusing a lot of our attention on, and because that is the SI unit of energy. 1 joule of heat raises the temperature of 1 gram of pure water 0.2390 degrees Celsius. So 1 joule equals 0.2390 calories, and 4.184 joules is equal to 1 calorie. So next we have heat capacity and specific heat. So on what factors does the heat capacity of an object depend? The amount of heat needed to increase the temperature of an object exactly 1 degree Celsius is the heat capacity of that object. The heat capacity of an object depends on both its mass and its chemical composition. The greater the mass of an object, the greater its heat capacity. The specific heat capacity, or simply the specific heat of a substance, is the amount of heat it takes to raise the temperature of 1 gram of that substance 1 degree Celsius. Water has a very high specific heat compared with other substances. Metals generally have low specific heats. You can think about like an aluminum can. An aluminum can, if you put cold liquids in it, the can feels cool. And if you put a hot liquid in it, it feels pretty hot. And that's pretty quickly because metals have a low specific heat. So we can talk about the specific heat of water. Water in lakes and oceans absorb heat from the air on hot days, and they release it back into the air on cool days. This property of water is responsible for moderate climate in coastal areas. So think about a pie. The crust and the filling, when you bake a pie, are initially at the same temperature, right? They're in that oven at, say, 350 degrees. The crust and the filling are 350 degrees when you take it out. Although the filling, which is mostly water, has a higher specific heat than the crust. And that's why when you take a pie out of the oven, you have to let it rest for so long. The crust might cool off, but since that filling is mostly water and water has a high specific heat, it takes a lot longer for that filling to cool down. So we can also calculate specific heat. And so we can look at this equation, C equals Q over M times delta T. And we are going to see that equation generally written as Q equals MC delta T. And this has just been rearranged to solve for C, the specific heat. So Q is the heat expressed in terms of joules or calories. M is mass. Delta T is the change in temperature. And we know that change in temperature, or a delta, implies final minus initial. And the units of specific heat are either joule per gram times degrees Celsius or calorie per gram times degrees Celsius. So let's calculate the specific heat. So the temperature of a 95.4 gram piece of copper increases from 25 degrees Celsius to 48 degrees Celsius when the copper absorbs 849 joules of heat. What is the specific heat of copper? So we know from the last slide that our equation is C equals Q, or the heat, over M delta T. Now it says that the copper absorbs 849 joules of heat. Since it absorbs the heat, we know that this is positive 849 joules. And we have 95.4 grams of copper. And our delta T is final 48.0 degrees Celsius minus the initial temperature, which was 25 degrees Celsius. And then we just calculate this out, and we get a specific heat of 0.387 joule per gram times degree Celsius. So in review, energy changes occur as either heat transfer or work, or a combination of the two. During any chemical or physical process, the energy of the universe remains unchanged. The heat capacity of an object depends on both its mass and its chemical composition. Alright, that's it for section 1. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great rest of your day.